All right, guys, we're going to go ahead and get started. So I know that when I came to you last time, or maybe it was a couple times ago, I told you that I'd laid out the calendar for the year. I explained to you that initially I thought we were on track and that we were going to be done before spring break. Then I came back to you later and said, guys, there's a couple days that are going to bleed over, and consequently we're going to need to do some Wednesday stuff. And so I tell you this to give you sort of background behind my thinking and what we're about to do. Guys, I've graded your tests. And as I was grading your tests, it became quickly apparent that not only weren't you getting the questions right, but if I were to turn you loose on these, I don't think you could get the questions right. I don't think I could put these tests in your hands and say, guys, all that you need is more time and more exposure, and you could go home and rewrite these tests on your own. There are some fundamental misunderstandings about intermolecular forces that were large and shared enough that I didn't feel comfortable just going, guys, here's your tests, rewrite them and bring them back next time. So what I realized last night as I was finishing grading your tests was it wouldn't make sense to buy back time and exchange it for understanding. So guys, what we're going to do today is we're actually going to spend the day and we're going to go back over intermolecular forces. And then when we're done with that, we're going to spend some time and we're going to talk about the implications of this relative to boiling point, relative to solubility. Those were the primary things, and volatility, the primary things that were covered on the test. And then, guys, importantly, we're going to talk about how we talk about these things. Because, guys, remember, I started this unit with this, right? That this is always the lowest scoring section on the AP test. And that's true. And so I'm accustomed to groups of students not doing well on this, but you guys sort of pushed the envelope. You redefined not doing well. So we're going to gather around this. Guys, as I was thinking about this last night, I don't know quite what fell apart here. I think that part of it may be that just the disruption of the last 12 months is starting to catch up with us. If nothing else, it tells me that to be ready for the AP test, we have more work to do than usual. So with that said, guys, I would encourage you to grab whatever materials you want. I am purposefully not giving you your test back yet. Because, guys, what you don't need right now is answers to questions. What you need right now is understandings of concepts. And so grab whatever even if it's just note-taking stuff, guys. And we are going to start here, and we are going to start tearing apart intermolecular forces. And we're going to do it like this. So guys, this is actually how we ended the day when we were talking about intermolecular forces. And guys, please, along the way, this is not just me reteaching. Now that you have better understandings of what you're not understanding, please be aggressive about asking questions. So the way the conversation is going to start is we are going to go over all of these different intermolecular forces. And guys, we're going to talk about these one at a time. And then what we're going to do is we're going to start mixing these together, no pun intended. And it's at that point we can start talking about things like solution formation and stuff like that. So guys, let's start down in the very, very bottom right-hand corner. If you want to jot any of this down, feel free. If you don't, that's fine too. But guys, ion dipole so we don't need to do ionic bonding. So we're going to go all the way over here to ion dipole forces. Guys, let me just tell you right now, these were not on the test. There was nothing on the test that had anything to do with ion dipole forces. And yet many of you, in many instances, were writing about ion dipole forces. Guys, there was not a single ion on the test. None. So if you mentioned ion dipole forces on the test, guys, it wasn't even on there, which tells me that fundamentally you don't understand what ion dipole forces are. So guys, let's break this down and talk about it. First of all, let's figure out what dipoles are. So guys, what has to be true of a molecule in order for it to have a dipole? It's got to be non-symmetrical, right? So if a molecule is non-symmetrical, it is then bent in such a way that it has an imbalance in electron sharing, which creates a dipole. Is that fundamentally a shared understanding? Okay, so then guys, where do we see ions? What is our traditional setting when we talk about ions? Salts. Guys, ions are things with charges. This is something you should have walked out of general chem. I'm teaching it to my Gen Chem kids right now. Guys, ions are atoms with a charge, or molecules with a charge if they're polyatomic. But guys, fundamentally, ions are things that are charged. So when we talk about ion dipole forces, what is really the only context in which this even becomes an issue? Dissolving salts in water. Guys, that's it. That is where we talk about this. So if you remember, and I know that all good things lead to the video, right? So guys, if you remember, this is the only place, sorry, just a second. This is the only place, oh, it didn't play. Play. It wants to play on its own. Here we go.
Interact with the ion.
Guys, that's it right there. Those are ion dipole forces. And that's the only place you're going to see ion dipole forces in the context of this class is polar molecules like water dissolving things like salt. So again, if there's no ions, you can't have ion dipole forces. Is that okay? We good there? Okay, so anything you need to talk about with ion dipole? Guys, please ask questions. So let me turn the question to you then. Guys, more than 50% of you, at least at some point on this test, identified what was going on as being attributed to ion dipole forces. What did you not understand previously? Can you help? Should this happen in the future? Because I think next year might be as weird as this year, because this year's been weird too. Guys, what can I do to help cut down on this misconception? Because I've never seen this before. Go ahead, Em. Okay. Okay. So I think, okay, so what you're saying is 1 is time and 2 is question clarification. Okay. Okay, go ahead, Matthew. Right. Right. Here come the gases. That's interesting.
That's kind of how I felt personally, because it felt like a shift in the direction.
Okay.
And we went to take the test, and that direction was not on the test. Does that make sense?
It does. I mean, 40% of the free response was gases.
Right.
But no, I understand what you're saying. I mean, I appreciate what you're saying, and I appreciate too what you said previously about the idea that we were making up for last year, right? Because last year we didn't do gases at all, so we did have to hit it a little more heavily. But that still doesn't help me understand how you guys were applying ion dipole interactions to a setting where there were no ions. That's still, yeah. Okay. Okay. Yeah. Yeah, absolutely. And that's an interesting observation too that I'd like to chat about. Guys, understand that what you're talking about there is not uncommon. Every time you touch a concept again, you're always going to be bringing things out of that material that you didn't see before. I mean, I remember when I started my freshman in college taking chemistry, and I remember Dr. Guzzo, my freshman chemistry professor, got up there and he said, the only difference between you guys and me with the PhD in chemistry is I finally understand freshman chemistry. I was like, dang. But really, it's true that as you move further and further along in any particular discipline, really, if you think about it, what you're doing is you're getting a better and better understanding of the fundamentals. And so don't be surprised as that becomes the case. Also realize that's what makes the way that we approach the AP test so effective. Because, guys, you're going to have 2 more touches on all of the material that you've already learned twice. Think about it. General chemistry, for the most part, all we've been doing is in AP is going back over Gen Chem and digging deeper into it. And then, guys, we're going to start in a couple weeks reviewing for the AP test outside of class while we're still learning new material. That's going to be your 3rd touch. And then, guys, after fall or after spring break, you're going to get a 4th touch when we start taking and tearing apart AP tests. Which, Emma, kind of speaks to your observation as well, that sometimes it's just hard to know what the question's saying. And we're going to work on that now, but we're going to work on that a lot after spring break as we start tearing tests apart. So, all right, are you guys okay on ion dipole? Okay, so now, guys, moving back, let's do, down at the bottom then, guys, the next one that we need to talk about is hydrogen bonding. Many of you think that anytime there's hydrogen bonding. Guys, that is not the case. And let me offer another suggestion. Guys, Spencer, wait on that, please. Let's not call this hydrogen bonding. Could we use the word hydrogen forces? Guys, the reason that I think that that's going to be better for you is many of you during the test talk about bonds breaking when things boil or when they evaporate or when they dissolve. You're talking about bonds breaking and reforming. Guys, boiling, melting, dissolving, all of those are physical changes. They're not chemical changes. You're not rearranging bonds. You're reorganizing intermolecular forces, with the exception of dissolving salts. That does break down the ionic bonds. But guys, those are physical changes. So you've got to draw a distinction in your mind between bonds and intermolecular forces. Yeah. 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 Can I couch that for just a second, Ronnie? I want to talk a lot about how to talk about this. But before we can talk about how to talk about it, I need to make sure we know what we're talking about. Yeah. So let's I want to get there. And actually, you're going to see in a minute, I stole one of your answers to a question and I typed it out. It's actually one of Gage's. So Gage, you'll see it. It was great, but needed work. And we're going to tear it apart and we're going to figure out how to make it better. So guys, let me show you an example of something that I saw in the test. So imagine that methane dissolves in water. It does. But imagine that you're dissolving methane oops. Oh, here we go. Because imagine that we're dissolving methane in water. And it doesn't dissolve a lot, but let's pretend that it does. If this did dissolve, would this be hydrogen forces? Guys, it's not. So we need to talk about what has to be present in order for hydrogen forces to be at play. So guys, obviously there has to be hydrogen, but that's not the extent of it. What has to happen is that these covalent bonds have to be shifted so closely to a highly electronegative element that what we actually end up with is what we call naked protons. So we end up with a positive charge here and a positive charge there, which are really the nuclei of the hydrogen atoms that are no longer, can I not do that? That are no longer fully encased by the valence electrons that they're sharing. And guys, these points of high positive charge, because they really are naked nuclei, are very, very attracted to regions of strong negative charge. And those regions of strong negative charge could simply be the unbonded electrons on a neighboring water molecule. But they could also be the electrons hanging off the side of a pyridine molecule. You see the electrons there on the nitrogen? That could also be an example of a place where we could get hydrogen bonding with water, because the naked protons on the water can actually be attracted to these electrons hanging off of the pyridine. Yeah. Yes. Good. Yes. Yes. Then it's dipole-dipole. Yep. So then, because remember, water is not symmetrical, so it has dipole forces, right? It has dipoles. So because water has dipoles, if that thing that's dissolving does not have doesn't have those high points of negativity, the electrons that are unshared, then it can still dissolve simply through dipole-dipole interactions. Well, we got to be careful, because, like, for example, if we look at something like water, and then if we look, I don't like the way I drew that. So if we look at something like water, and then if we next to this draw an ammonia molecule, so we would have the opportunity for hydrogen bonding to take place here. Highly electronegative element bonded to hydrogen, naked proton attraction right there, right? So that would be the possibility. So the force that would cause ammonia to dissolve in water would be hydrogen bonding. But understand that what if we had ammonia, and then if we had ammonia trying to dissolve something like, let's say an alcohol? Maybe that would be, Matt, let me see if this is kind of what you're getting at. So say that we're using that to dissolve an alcohol. Would this be the opportunity for hydrogen bonding? It actually is. Because here we have naked protons, here we have unshielded electrons, and then here we also have a naked proton, because again, we've got oxygen bonded to hydrogen. This is highly polar. This would create a naked proton. So we would have the opportunity for hydrogen bonding in both directions. Is that okay? Braden, go ahead. Yes, and that's important, that for there to be hydrogen bonding, it has hydrogen forces. It has to meet both of those requirements. You've got to have a nitrogen, oxygen, or fluorine bonded to a hydrogen. That makes the naked proton. But then that other thing has to have unpaired, unbonded electrons that the naked proton is attracted to. Is that, yeah, go ahead, just a second. Then they wouldn't be naked, because, so the naked do you mean the naked protons or electrons? Say that, it doesn't matter. If you've got unbonded electrons, what if those electrons are on a metal? We don't need to worry about that. So if you've got unbonded electrons, so like for example, let's look at hydrogen sulfide gas. So H, S, H, H, boom, boom, boom. So H2S, hydrogen sulfide gas, right? It's sulfur is a group mate with oxygen. It looks like water. And then we've got water. Would this be hydrogen bonding? And the answer is yes, because you've got naked protons here, you've got unbonded electrons there. That would also dissolve through hydrogen forces. Is that okay? That's exactly right. Yep. Yeah, but here's the interest. We'll talk about it in a minute. They didn't require that you say hydrogen bonding on that one. They would have allowed you to say dipole, but hydrogen bonding is actually the most correct answer. Emma, go ahead. Oh, it did, and holy smokes, I got some interesting answers. Let's talk about it when we talk specifically about the test. Yeah, some of you guys actually turned the molecule into water. It was magic. Okay, so then guys, moving along, we've got dipole forces. Oh yeah,
Really quick,
yeah, please, yeah.
So it's always between like a naked proton and unfilled electrons.
Unbonded electrons, yes, yep.
So if you were just talking about like a water molecule, because that's H2O, which bonds to the oxygen, would you say the hydrogen forces are present, or does it have to be between two molecules?
Big time out, y'all. We're going to talk more about this later, but that is key to what you guys aren't doing well. So guys, Donnie's question, and I'm going to babble through it so Donnie, let me get to the heart of what you're saying. Guys, you ready? A water molecule does not have hydrogen forces. Just let that rattle for a minute. A water molecule does not have hydrogen forces. A water molecule has the potential for hydrogen forces, but it has to be a relationship with something else that has the potential. So what is it that holds water together? Hydrogen forces. But that molecule itself doesn't have hydrogen forces. There has to be something for it to exhibit those forces with. That's going to be critical to how we talk about these answers. Because guys, some of you were saying things like the dipole forces of water are attracted to the dipole forces of this other thing. No, they're not. Water has the potential for dipole forces. This thing has the potential for dipole forces. The attraction between them is dipole. But it doesn't, we'll talk more in a minute. So guys, dipole forces, you good on that one? Molecules that are not symmetrical, that then have imbalances in charge, that then are attracted to other things that also have imbalances in charge. Is that okay? Okay. And then guys, finally, London dispersion forces. It's interesting that a lot of you chose to call them London dispersion forces. That's totally fine. The AP authors understand that. Induced dipoles is fine as well. But guys, fundamentally, everything has induced dipoles, right? So when we talk about induced dipoles, we're talking about oh, no, I didn't leave it in there. So guys, let me grab this. Are we okay with induced dipoles, or do we need to see pictures? So guys, maybe we just draw a picture. So the idea is this. So say, for example, we've got a molecule. Why do I keep going there? Let's not even do that. So guys, let's take a molecule like chlorine, diatomic chlorine. Very, very, very symmetrical, right? So how is it that something like chlorine can exhibit intermolecular forces? And again, the idea that we talk about are instantaneous dipoles. Guys, at any particular moment, this electron distribution could be lopsided. If that's the case, it creates a dipole. And guys, that dipole then can actually induce dipoles in neighboring molecules. And that inducing of dipoles actually creates intermolecular forces throughout a substance, which can lock these things together as liquids and solids. Is that coming back to you? Then let me ask you a question. What does it look like if you try to dissolve chlorine gas in water? What intermolecular force is at play as chlorine tries to dissolve in water? So guys, let's chat. What is the only intermolecular force that's possible in diatomic chlorine? Induced dipoles. I'll just call them LDFs, London Dispersion Forces. What is then the intermolecular force that water has the potential to exhibit? Dipole forces. We can't talk about hydrogen bonding because clearly this doesn't qualify. So guys, does chlorine dissolve in water? And the answer is no. Why not? Because the dipole London dispersion intermolecular force between these is not strong enough to get it to dissolve. Guys, that's the way you talk about this. Some of you are talking about has nothing to grab onto. Because that's, well, maybe that's conceptually the way that you think about it. That is not the way that we intelligently talk about this. So the idea is that chlorine does not dissolve in water because the London dispersion force, dipole, intermolecular force, is not strong enough to cause this to dissolve. Yeah.
Why doesn't the chlorine qualify for hydrogen forces?
Because it doesn't have hydrogen. It doesn't have a naked proton. Oh, I see what you're saying. That's an interesting question. No. I do understand what you're saying. No, I get what you're saying because you've got the naked protons and then you've got a bunch of electrons that are not bonded. You know, Donnie, I may have just talked myself into a corner here, because I'm making this stuff up on the fly, right? And so I chose something that was symmetrical and therefore nonpolar. You know, that may dissolve because of hydrogen forces, now that I say it. You know what? Let's couch that one for a second. Hey, so guys, I know that for you, you found something unique and maybe a little edgy and oh my gosh. But if nothing else, you're coming to understand why it's so hard to write questions for AP tests. And understand, I'm faking this in front of you, and I'm so glad that you asked the question because there's something to be learned from the answer. Because there is perhaps, and I would have never caught this, because I was looking at diatomic chlorine simply as something that is symmetrical. And I chose chlorine because it was the simplest symmetrical molecule that I could think of on the fly, because I was going to use methane, but we're sick of talking about it. So guys, there is perhaps the possibility that this could be the case. I'd like to look it up because I actually don't know. But what we can draw from this is this idea. Molecules that are not symmetrical. If you would prefer, we can use benzene, which was on the test. Now we've got rid of the electrons. Now what intermolecular force is at play? Now we've only got induced dipoles. Why does benzene not dissolve in water? And guys, the way that we talk about this is water is water is not symmetrical and therefore polar. Benzene is highly symmetrical and therefore only capable of exhibiting London dispersion or induced dipole forces. The force of attraction, the dipole London dispersion force attraction, is not strong enough to cause the benzene to dissolve in water. So Donnie, while your observation is great, and I would really love to go back and look at this, guys, don't choke on gnats swatting at camels, right? So we got our choke on camels swatting. We got to be careful here that we're focusing on the big ideas. So I do love the question, but let's make sure we're chasing the big ideas. Okay, but that was a big idea, but you get the idea. Are we okay there? Yeah. No, and so what we need to do is we need to talk about this force. So because water is not symmetrical, it has the ability to create dipole forces, right? This is not polar, and therefore the only intermolecular force that it could exhibit would be London dispersion forces. And so why does benzene not dissolve in water? And the answer is the dipole London dispersion force interaction between these molecules is not strong enough to cause the benzene to dissolve. Prior to that, we would need to establish the idea that water is not symmetrical, therefore polar, and that this is symmetrical and therefore can only exhibit London dispersion forces. And we'll talk more about that in a minute. You guys okay? We good? Yeah, Braden? Yeah. Yes. That's totally fine. And some of you did that successfully. Yeah, and that's not wrong. You can say that benzene exhibits London dispersion forces. The forces that hold the water together are hydrogen forces. And then the dipole London dispersion force between them is not stronger than those other forces. That's totally fine. And some of you did do that successfully in instances. The place where many times it fell apart was the talking about the interactions, the talking about the coming together of the two. If you want to talk specifically about your answers, I'd love to do it. So, but yeah, we'll see. Yeah. Give me an example. Oh, like oil and water. So the idea is, oil and gasoline, for example. So what's going on there is you've got the oil and the gasoline inducing dipoles in each other, and those interactions are actually strong enough that it does allow them to dissolve. Absolutely. Yeah, and they allow them to dissolve. That's a great question, and the answer is, in theory, it could a little bit, but then that force is not strong enough to break the hydrogen forces that are already in the water. Which is, Braden, kind of getting to what you were talking about earlier. You guys okay? Yeah. Oh no, water by itself is held together by hydrogen forces. Yeah. The molecules are held together by... So a water molecule doesn't have hydrogen forces. It has the potential for hydrogen forces. When we get a bunch of water molecules together, that's where we get the hydrogen forces. Okay, so let me show you an example maybe of what we're talking about there. So guys, let's go here and let's take a look at this. So, guys, looking at the test and looking at question 3A, I already showed you pyridine. And, guys, looking at question 3A, it says this. The structures of pyridine molecules and benzene molecules are shown below. Pyridine is soluble in water, whereas benzene is not. account for the differences in solubility, you must discuss both substances in your answers. So guys, understand we've got a complex question there. And Emma, you're talking about how to, you know what, maybe I should put this up on the wall. So guys, this then is the question. We've got pyridine on the left, we've got benzene on the right. And you'll notice that it says we must discuss both in our answers. And so guys, do you see that we actually have two answers here? They are asking us to talk about why does pyridine dissolve and why does benzene not dissolve? And in each one of those answers, we need to discuss both substances. So guys, as we're structuring our thinking then relative to this, we need to structure our answers in a way that meets the requirements of the question. So we take these one at a time. Guys, why does pyridine dissolve in water? Well, what do we know about water? Is it polar? Water is polar. Water is not symmetrical and therefore polar. What about pyridine? Is it polar? It is polar. It is not symmetrical and therefore polar. And once we've established that by talking about both substances, then we can say that the dipole forces that exist between pyridine and water are strong enough to cause pyridine to dissolve. Now with that said, you could have called that a hydrogen force because technically it could be because you've got naked protons on the water and you've got unbonded electrons on the nitrogen, but they would have let you get away just by calling it a dipole force. But in either case, you need to talk about water is not symmetrical, therefore polar. Pyridine, not symmetrical, therefore polar. The dipole or hydrogen forces between them allow that to dissolve. Now we come over here. Why does benzene not dissolve? Water, still polar. What about benzene? Benzene is symmetrical and therefore non-polar. So what will the force of attraction be between water and benzene? Induced dipole forces. Those are not strong enough to cause the benzene to dissolve. Do you see how to structure that? Go ahead.
So the induced dipole and dipole, they have a force together. I just feel like we never knew how to stay them together.
Okay.
When I kind of said like, water can only do dipole, and benzene can only do induced dipole. I never said like there's a force between them. I just said there's no force between them.
Which isn't true, right? Yeah, so let's go here and let's talk about this. So guys, this is an answer that, again, I'm just gauged, and it was great, but let's talk about how it could be better. It says pyridine is asymmetrical and has dipole forces, which more strongly attack with the dipole forces in water and make it soluble. Benzene is symmetrical and only has weaker London dispersion forces. The dipole forces in water are hardly attracted to these forces, so benzene is not soluble in water. Sounds great, right? Because you'd actually not get credit for this. So let's talk about how we could clean this up and make it better. So guys, I would suggest that the place that you would start is right here. It's not the dipole forces in the pyridine that are attracted to the dipole forces in water. That dipole idea is describing the forces within the water and the forces within the pyridine. Because the idea here is that we need to talk about them coming together. So really what I did to sort of doctor this up is I got rid of one of these dipoles, and then I said pyridine is asymmetrical and therefore has the potential or could create dipole forces which are more strongly attracted with the dipoles in the water. The dipoles, let's just get rid of forces. So we would go dipoles. So get rid of this, get rid of this, get rid of forces. And then let's see how it reads. Pyridine is symmetrical and has dipoles. Has dipoles which more strongly attract with the dipoles in water and make it soluble. Do you see the distinction? Does it feel like we're being nitpicky? Because, guys, the distinction is big. We need to talk about what water potentially could do, what the pyridine could potentially do, and then the way that those interact together. So let's go on. So benzene is symmetrical and only has weaker dispersion forces. How do we clean that up? Benzene is symmetrical and therefore, but it exhibits induced dipoles with itself, and so benzene is symmetrical and can only exhibit weaker London dispersion forces. The dipoles in water are hardly attracted to these London dispersion forces, so benzene is not soluble in water. Do you see the distinction? So guys, the big idea is when you're answering these questions, you want to focus on what can water do, what can pyridine do, what do they do together? What can water do, what can benzene do, what do they do together? Yeah.
Could you also talk about polarity instead of dipoles? Like pyridine is polar, water is polar, so they're more attractive to dipole.
Absolutely. But you'd have to get to that bottom thought that says dipole between the pyridine and the water. Yeah, absolutely. So if you had just said pyridine is polar, water is polar, therefore it dissolves, you haven't identified what they do together. So you need to talk about the force.
Therefore, they can exhibit the dipole.
Correct, exactly. Yep. What else, y'all? Yeah, Emma. Yes. So you need, and actually I can show you the key to these. They expect that you would say that the induced dipole forces between the water and the benzene are not strong enough to cause it to dissolve. Yeah. Oh, yeah. Or dipole London dispersion force. Yeah. Yep. What else, y'all? You guys okay? Yeah. Yeah. Oh no, yeah, no, they would definitely, yeah. In this particular instance with the pyridine, they were loose, but no, if and I don't know, everything that we use on our, should I tell you this? Everything that we use on our tests are freely available online, including the keys. And if you go back and look at the keys for these, it mentions hydrogen forces extensively when it's appropriate. On that particular question with the pyridine, it didn't require it, but parenthetically it said they could call these hydrogen forces. But when it's really clear that that's what it is, and we'll look at some of those, it needs to be there. Yeah. You guys okay? Okay. So guys, with that said then, what I want to do is I want to give you your tests, and then we're going to talk.
in the middle, which makes positive. Okay.
Oh, sorry. All right, so guys, I would like to gather us together again and talk over some observations relative to the test. So guys, we're going to talk about the free response, and we're going to sort of tear this apart a little bit. So looking at questions A1AI and 1A II. So, first of all, guys, notice what this question doesn't say. You'll notice that there is nothing there that it says explain. Yeah. Why? That's really odd. Oh, wait, I was looking at it. Oh, that's why. Sorry, thank you. So guys, notice that on 1AI and 1A II, it doesn't say explain. Don't. You could not even write sentences on the AP test on that question and be just fine. What are the forces? What are the forces? Then guys, looking down at B, it talks about glucose is soluble in water. Glucose is soluble in water, cyclohexane is not, and please explain. Guys, notice what this question doesn't say. So let me give you the context for this. This was a question off of a test pre-2014. What happened in 2014 is they radically changed our curriculum and they made it much more conceptual. And they were not good at writing questions. If you compare this to question 3A, the one about the pyridine and the benzene, guys, it's exactly the same question. Different players, but it's almost exactly the same question. But notice how they phrase the question differently. It says, account for the differences and you must discuss both substances. Guys, it turns out that they had actually created an inequality in the class because those of us as teachers that were actually looking over the answer sets knew that in order to get full credit for these, you had to talk about both substances in both cases. But guys, when this question was written back in 2014, they assumed kids knew that, but they didn't they didn't come right out and say it. And kids were missing points and they didn't know why. So they're now mentioning it by name because that's not why you missed points on question 1 if you did 1C or 1B. But guys, please understand that when you go back to do 1B, you need to mention both substances in both instances. Okay? Then guys, again, I've got a big note to myself down here at the bottom. Even on page 1, we started seeing stuff about ion dipole forces. Even up in 1AI and 1A II. I hope now you understand why that's not the case, and if you don't, please talk with me. Then guys, turning the page again. Looking at page 2. So guys, question 2, letter C. Guys, when you're answering this question, be sure that you read the question carefully. It says dichloromethane has a greater solubility in water than carbon tet. It says account for this observation in terms of the intermolecular forces between each of the solutes in the water. See how this question's getting better? That now they're directing you to talk about the IMFs between the solutes in water, which is what we just talked about, right? We need to be talking about the forces that exist between the solutes in water. So be careful about how you do this. Guys, in addition to that, I had a not small number of you say that the force of attraction between dichloromethane and water is hydrogen bonding. Look at dichloromethane. You see its Lewis dot structure? Do you see why hydrogen bonding is not a possibility? And you're going, wait, there are unbonded electrons on that chlorine, because it doesn't work that way. I think we're getting closer to maybe the answer about chlorine, diatomic chlorine dissolving in water. Those electrons around those outlying atoms are not available for hydrogen bonding. So that would just be a dipole-dipole interaction. That's not a hydrogen force. Okay, so then down below that, letter D, guys, again, make sure that you're talking about the forces in both substances. But please notice too, guys, that this is counterintuitive, right? Letter D is counterintuitive. Let's talk. Looking at dichloromethane, what is the force of attraction within dichloromethane? Dipole-dipole. What are the forces of attraction within carbon tet? Induced dipoles. Which are stronger? Dipole-dipole. So why does carbon tet have a higher boiling point? Do you see the problem? Guys, they love to put you in situations like this where the data is counterintuitive. What we have going on here is that the carbon tetrachloride's induced dipole forces are stronger than the dipole-dipole forces in dichloromethane. The reason is because carbon tet is so large, so heavy, that it's very polarizable. But this is counterintuitive, and they love to put you in those situations. Well, and so that's the thing. You don't have to talk about the counterintuitive nature of it. What you would need to say is this. Dichloromethane is nonpolar and therefore exhibits dipole-dipole forces. Carbon tetrachloride is symmetrical and therefore exhibits induced dipole forces. The boiling point of carbon tet is higher because its induced dipole forces are stronger than the dipole-dipole forces in dichloromethane. Is that okay? Okay. Then guys, looking down at letter E, if I may. So we've got this. And guys, I'm not going to call out some of the really interesting answers that I got. Just a second. Other than to say this. That's not right. This end of this molecule cannot exhibit hydrogen forces. Why not? Carbon's not strong enough to create naked protons. So guys, if you drew anything down here, it's just automatically wrong. Because the hydrogen forces don't come from the carbon end of this thing. It's these electrons being attracted to the naked proton on water. Now understand, they were open to some creative interpretations Come on. Oops. Some of you did something like, I don't even know if I can do it right, like this kind of. And realize, guys, it tells you specifically to draw dots on this one, right? Dashed lines. So you needed to draw a dashed line to show the forces. And guys, bottom line is the forces needed to be drawn between unbonded electrons and the hydrogen on the water. Also notice, guys, that it tells you to draw a water molecule. It means they just want one. So questions on that? Somebody, yeah? Yeah, so the key, and I mean, you know what kind of artist I am, right? But the key actually looked like this, without the circles, but it looked. And I probably should have drawn a little more space, but then a dashed line right there. You guys good there? Yeah. Sure. Right. And I think what I'm coming to find is I don't have a good explanation for it. Yeah, so for the same reason the thing that you brought up was Cl2, let me look into it. Frankly, the question has never come up before. Let me look into it. Yeah, but notice here, because it's a little contradictory, right? Because now we've got electrons on the side of oxygen, which kind of feel the same to us like electrons on the side of chlorine, right? But you'll notice here, they're not asking you what forces exist. They're telling you which ones exist and then asking you to draw them in. You guys okay? So guys, continuing on then to the next page. I think we've probably talked a lot about the pyridine question. Then guys, down below, looking at letter B. Structure of dimethyl ether and ethanol are below. Normal boiling point of dimethyl ether is 250. Ethanol is 351. Account for the differences. And hey, here it is. You must discuss the forces. Discuss both of the substances. Your answer. First thing I did is I wrote the data down above the structures. I couldn't keep it straight, so I wrote them down. So guys, let's talk. Looking at ethanol. What are the forces that hold ethanol together? They're hydrogen forces, y'all. You've got a hydrogen bonded to an oxygen, right? Classic hydrogen forces. Now guys, try this. Don't miss this. Dimethyl ether, one on the left. Symmetrical? No. Guys, this is not symmetrical. If you're not sure what I'm talking about, talk to me about this. Is water symmetrical? Water, it looks symmetrical, right? But we know that it's bent because we know that actually those unbonded electrons cause it to bend. Look at dimethyl ether. Same thing. Guys, they drew it for you straight, trying to sucker you in. Yeah, right. And the same thing's true here. Go ahead.
In ethanol, are you saying that you said the hydrogen forces?
Uh-huh.
Are you saying that's like the only forces?
So understand that we could also talk about dipole. We could also talk about London dispersion forces, induced dipoles, because they're all present. But notice the huge difference in boiling point. It's a huge, so what they're asking you to do is they're asking you to account for this difference. And the huge difference in boiling point is a function of those hydrogen forces. Anything else there, you guys? Okay, then turning over again. On number 4, are we going back? Go ahead. Correct. Yes. Yep, you got it. Yep. Okay, so then guys, turning the page again. Please, if you're going to use numbers, do math. You don't get to just write down the answers without doing the math. Also, guys, this, on question number 4. Please remember that molecules have never heard of Avogadro, and molecules do not know that they're ideal. So for example, on the first 2, when it asks the question, does this result depend upon the identity of the gas, or however it says it? A lot of you said things like, the identity of the gas does not matter because it's an ideal gas. Or the identity of the gas does not matter because of Avogadro's principle. Guys, Avogadro's principle describes the phenomenon, but it doesn't cause the phenomenon. So guys, in both instances, why does it not matter what the gas is? And then many of you who were getting closer to it said, because the molecules are insignificant. Well, no, they're important. They're there. And then some of you got even closer and said that the volume of the molecules is insignificant. But guys, you didn't finish the thought. Compared to what? And that's where you need to get to. The answer to why on both the first and second question are about the insignificance of the gas molecules themselves compared to whatever the particular context happens to be. Okay, but guys, please understand that guiding principle. Molecules can't do math. Molecules don't know Avogadro. Those are descriptions, but not causes. Okay? All right, and then guys, flipping over one more time. Actually, wait a second. No, I'm sorry. Guys, I want to go back to question 3 after the dimethyl ether and the ethanol. The one at the bottom. The one about the sulfur dioxide and the silicon dioxide. Because you remember we talked about this one directly in class? I even told you, guys, I'm going to tell you the answer right now, and you're still going to get it wrong on the test. And all but 2 of you did. So some of you remembered that it was a covalent network solid, but didn't understand the idea fully, but at least you wrote down the words. Guys, here's the thing we're looking at. Look at the difference in boiling point and melting point. It's stinking ridiculous, right? When things melt at 1800 Kelvin, we're no longer talking about intermolecular forces. 1800 Kelvin is not on the order of magnitude of the strength of an intermolecular force, even a hydrogen force, even an ion dipole force. Because we got to be talking about something radically different. And the radically different thing that we're talking about here are covalent network structures, like we see in something like diamond, where guys, if something is breaking apart at 1800 Kelvin, we've got to be breaking bonds. And the bonds that we're breaking in this instance are actually covalent network bonds. So silicon dioxide, which you may remember is sand. Guys, the silicons and the oxygens don't exist as discrete little packages. They covalent bond to each other throughout the entire crystal, and that's what sand is. What they were trying to do was feed you some data that went, oh crap, something crazy is going on here. And even if you had just said, melting SO2 is the breaking of IMFs and melting SiO2 must be the breaking of bonds because it's so high, they would have given you credit for that. They were asking you to look for the big ideas. And then guys, that last page, I'm going to let you think through that one and just leave it at that. So guys, let me explain to you where we're at right now. Guys, obviously there's work that needs to be done, right? And I really appreciate your vulnerability and going, hey, this is where I was at. Matthew explaining, wait, we did a lot of gases and then this came back to bite me in the butt. Emma sharing, hey, wait a second, I didn't really understand how to tear these questions apart. Guys, here's the deal and here's the difference. The experiences that you're having right now don't make you different, they make you late. And it's not your fault. Guys, understand that these experiences of, wait a second, I didn't know or I forgot about, Guys, normally we slay this dragon in October. We're dealing with it in February. It's just the reality of where we're at right now. And this idea of tearing questions apart and all these other things and sort of this unease with, wait a minute, what about chlorine? And I've got to come back, Matthew, I need you to join me. This idea about chlorine, and we're like, wait a second, I don't quite know. But guys, we've got to be comfortable with this. We've got to be comfortable with the uncertainty. We've got to grasp this idea that just because we didn't talk about it last time doesn't mean it's not going to be a lot on the test. Because you have been brought up in this broken academic environment that says all you got to do is just follow the teacher and everything's going to be fine. Guys, I can't protect you fully from the things that are coming down the road. Guys, there are not study guides for tests, because the minute I stick a study guide on the website, you guys go, okay, wait, if I can do all this, then I'm good. Maybe not. Guys, understand, we are chewing on a way bigger elephant than you guys are accustomed to nibbling on. And normally by this point in the year, the discomfort with that is gone. And we just understand that this is always going to feel weird and crazy and a little uncomfortable. And we all just move through it together, and we get to the AP test and it all works out great. So guys, again, we're not in trouble. We're just late to the game. But what I'm starting to get a sense is that some of you are going, I really don't care. I don't want to invest the time. I've got other things going on. I'm going to do this my way. And guys, that's going to be your choice. Here's what we're going to do. In 2 weeks, maybe next week, I'm going to bring to you, again, the same commitment form that I ask from all of my AP students. And guys, you are going to commit to whether or not you're going to take the test. And guys, understand that if you commit to take the test, guys, we are going to do the things that we need to do to get you ready for this test. And it's going to involve time, it's going to involve focus, and it's going to involve effort. And if that's worth it to you, then I'm going to invite you to engage, and we're going to work our tails off for the next 2 months, and you guys are going to crush this test. Now, guys, if you're looking at this, and I'm going to ask you to be totally honest, if you're just like, you know what, I don't care. This isn't my gig. I'm not probably going to take chem when I get to college anyway. I could use my time better other places, or I'm just so beat down by all this COVID crap that I just don't care anymore. Guys, I'm going to ask you to own that. And I'm going to ask you to step out of the way so that those of us that are engaged and want to move on are ready to do that full steam ahead. So there's probably going to be a separation in the room, and it's going to be palpable. Some of you are going to be like, you know what, I'm done. I'm going to just ask you to please not interrupt or distract or get in the way. I'm going to sort of push you to I'm going to push you to the side. And guys, we're going to keep cruising. Because guys, we have a lot of work to do. That became very, very apparent right here, not only in your answers to these test questions, but in the concerns and the issues that we're facing as we're talking today. So, guys, here's what we're going to do with this test. You are going to redo it for full credit in groups, okay? I'm going to allow you to redo this test for full credit. So you've got I haven't given them to you yet. Guys, here are the rewrite forms. The rewrite forms are exactly the same forms as the test, the thing you did the test on. And guys, I'm going to allow you to redo this test in groups for full credit. I'm not going to give you 2/3 points for what you rewrote. I'm simply going to grade this again, and that's going to be your grade on the test, and I'm encouraging you to do this in groups. That's why I'm not asking you to leave. Do you guys pick up on that? Sophie hasn't taken the test yet. That's why I allowed you to stay. Guys, that's the deal. Your score on the test that you have in front of you has nothing to do with the test. You are going to redo this in groups if you choose. And guys, that's what I'm going to grade for full credit. So that also means that you need bubble sheets. Let me get those for you. And guys, you're going to turn these in to me next Thursday. I do want your old tests back as well, because those are not public domain. But guys, you're going to do you understand, right? Okay. Multiple choice as well. Yeah, so guys, let's let's talk about this. So I understand that the minute I say you can't use this, it's putting you in a position where you could end up cheating. I would suggest that the best thing for you would be this. You may use your old test, and you may use other people. I would suggest that using your book, the internet, notes, things like that, certainly, and I just told you, the answers to these are all online, right? That's cheating. Because guys, the reason that I'm inviting you to do this again is because I want you to learn the material. I don't give a crap what you get on this test. I want you to beat the bajinkers out of the AP test, right? So let's handle this in a way that accomplishes that best. So old tests and work with each other. Yeah. Yeah. I mean, because I don't want to have to compare the two. Bye, Keely. So guys, let's take a break and we'll come back. You're redoing the whole test. I'm not going to look at your old test.